Hello everyone, and today I would like to give you an introduction about our EAG battery lab. And for today's agenda, I would first give you some introduction about Eurofins EAG laboratories as a whole, and then we'll move to the EAG one-stop battery testing service we offered. And after that, our battery scientist, Dong Zhang, he is going to give you an example of the failure analysis and some deformation and analysis we have done. And eventually, you ask questions. So for EAG, so we have over 40 years experience and serving multiple industries and focusing on materials catalyzations. And we have more than 20 plus facilities located in the United States, Europe, and Asia. And we provide the service to over 5,000 clients. And we are very strict on our IP and also take care of the secret of our customers. And we are certified across multiple industries and markets. And we have a business continuity plan which can ensure our operation even when we're facing the disasters or some worldwide redundancy. And also, EAG is financially backed up by Eurofins, which is our parent company, who is a multiple billion-dollar global leader in scientific service with a portfolio of over 200,000 validated analytical methods. And in this map, you can see where our 20 plus locations distributed. So majority is in the United States, and we can see there are several in the Bay Area in California. And the star is where our new battery lab located. And also we have several laboratories in Europe, and also many of them are in Asia to serve the local customers. Talking about our service scope, and we have a wide range of service we provide, and like advanced microscopy, enhanced SIMS, also advanced spectroscopy. And also we can do failure analysis on a wide range of devices. And we are very strong at materials characterizations. And our chemists can do a lot of chemical analysis for your materials, including purity and survey. And our microelectronics testing already served the semiconductor industry for a long time. And also we can do reliability testing for your devices. And we also support a lot of legal jobs and for a lot of customers. In the next slide, you will see this chart. It's a very beautiful chart. And here we call it SMART chart, which means spectroscopy, microscopy, analytical resolution tool. And it shows the techniques we have at EAG. This SMART chart allows us to compare the spot size here and the detection limit of each technique. The techniques are color-coded according to the description at the lower left. For example, dark blue area provides elemental information primarily, while green shows imaging information. The x-axis shows the range of spot size from 1 centimeter at the right down to 1 angstrom at the far left. The y-axis shows concentration either in atoms per cubic centimeter at the left or atom concentration at the right, that ranging from 100% at the top down to 10 parts per trillion at the bottom. So within this box, you can select your technique based on the detection limit you need and the size of your area of interest. Outside the box are techniques that don't quite belong in the chart. The techniques on the right, for example, don't necessarily have a small size associated with them. They are basically bulk composition techniques that may consume your entire sample, and they have the detection range shown from top to bottom. The techniques at the bottom are basically imaging techniques that do not provide composition per se, but they do have relevance with respect to the spot size on the x-axis. And if you click that QR code, you can request for a poster size copy of this smart chart. And let's go back to our main topic of today, and that's the battery testing service we provide. So here's the scope of a battery testing service at EAG. We can definitely start from the raw materials, and we'll provide trace elemental analysis, which can identify and detect unwanted impurities in your raw materials for battery raw materials providers. And during the battery manufacturing process, our elemental and chemical analysis can provide very useful information about electrochemical process. And for the device application side, materials analysis can investigate the root cause of battery-related failure mode. And recently, there's a lot of companies, they focusing on recycling the batteries. So our materials characterization can also ensure those recycled materials are of the highest purity. And talking about what kind of sample we can deal with. Here is just a snapshot of what we can really analyze. We can take full batteries, just like as small as coin cell to as big as EV packs and modules, coin cells. And we can cycle those batteries. I will introduce our cycle room later. And we can also do a series of non-destructive analysis, like the blue LED scan, CT scan, and X-ray, and also the electrochemical impedance spectroscopy to analyze the health of the battery. And also, if it's needed, we can also disassemble the battery, extract the components like electrolyte, cathode, anode, or separators. And we have, you can see here, we list various of techniques we can use to analyze and all these components. Furthermore, we can even extract the raw materials from the components, like the cathode, raw cathode powder, and anode materials from the electrode, and then also do the further characterizations like particle size, purity survey, and XRD on those materials as well. And next, talking about our new battery lab, which was opened last May. And here is just a map of our battery lab, which is located at Sunnyvale, California. Here you can see in this battery lab, we have a big cycler room. In the cycler room, we have all sizes of cyclers, including coin cell cycler, cylindrical cell cycler, prismatic cell cycler, module cycler, and even the full pack cyclers. So we can handle all sizes of batteries or battery module packs. And we also have a dry room. This is a heart of the battery lab. In the dry room, we have argon glove boxes. And in this dry room can let us to assemble coin cells, pouch cells, and also disassemble all sizes of cells for the failure analysis or material calculations. And we also have a small characterization lab in the house, including several types of techniques like benchtop SEM, which also equipped with EDS. It can give provide elemental information, and this SEM also equipped with airless transfer box, which means we can disassemble the battery in the glove box and then mount the components into the airless transfer box. and then directly transfer it to the SEM for characterizations, which can avoid exposure to any air moisture. So we'll maintain the status of the materials from the battery. And also we have digital microscope, also we equipped with elemental analysis module. And we have, as I mentioned, we have 3D blue LED scanner, can scan the structure of devices or batteries. We have electrochemical impedance capability, and we have 2 particle size analyzers. One is laser diffraction, one is dynamic light scattering. Combine these two, we can analyze particle size as small as 1 nanometer to as big as 2,000 microns. If it's bigger than that, we can use our digital microscope and then do the photo imaging analysis, and we can still analyze the particle size, even if it's bigger than 2 millimeter. And we also have a residual gas analyzer, which is designed to analyze the swollen pouch cell and then to determine what kind of gas generated in the pouch cells. And we have done many of these type of jobs for the failure analysis purpose. And also we have an auto titrator, which is capable to do Karl Fischer titration and electrolyte conductivity titration and determine the HF amount or the carbonate. And also we are able to do the tap density, bulk density, etc. So talking about the service we can offer from our battery lab or within the whole EAG, we are able to cycle, as I mentioned, various of type of batteries, modules, and packs, and then under the controlled environment, since we have 3 environmental chambers, can control the temperature and humidity during the life cycle of batteries. And we are able to do non-destructive techniques like CT scan, EIS, or blue LED scan. And we can tear down all sizes of batteries as long as we can fit it into our dry room or the glove box. And then we can extract the anode cathode separator or even the binder electrolyte, and then do further categorizations on those materials. And we have a full equipment line to build coin cell from scratch from the raw materials. So we are able to make slurry, we're able to do the coating, to make the coating, and then to make the electrode, eventually assemble coin cells or even part cells in the near future. And we have done many battery failure analysis, and like swollen battery, and battery with malfunction, and also battery with containing some impurities. So later on, Dangjiang will give you an example of that. And also we have air-free transfer systems we can connect to our glove box and dry room, and which can using for SEM, TEM, and Durabin FIB, and XPS, and several other techniques as well. All right, that's summary of the battery testing service we offer within EAG. And next, I will transfer to Dangjiang, so he will give you an instruction of the failure analysis example of what we have done before. Thank you.
Thank you, Daniel. Hi, everyone. So my name is Dangjiang, and now I would like to present you a failure analysis case study. So the data that I will show you today is none of them are client data, because we really value the confidentiality. So all of these data are the data that we produce intentionally, and we intentionally failed the battery and then analyzed it as a possible project that we get from our clients. And what we will see in this project is what we do actually. We start with non-destructive analysis to see whether anything going wrong with the device or the battery itself, by looking into 2D X-ray images, or if needed, 3D CT scans. And then if the battery is swollen, in many cases, failed batteries can generate gaseous species in them, and it is really important to analyze those in order to understand what caused this issue. We have a semi-quantitative RGA equipment available in our battery lab, so we are looking into the the composition of the gas inside the battery. And then we do a full teardown to isolate components and individually characterize them, either looking for compositional changes, structural changes, or mechanical changes during the operation. And also for these components, we can do particle size analysis or pore analysis. I will also show a few data about this, but not only for the components, we can also do this for the raw materials, like particle size analysis can be also useful for the raw materials as well. And we also provide electrolyte characterization too, with the help of GCMS and all the other techniques to understand what type of solvents are being used or what salt components, what salt composition is available in the electrolyte. And let me start with the non-destructive analysis part. So this is the image from the 2D X-ray. Of course, when we first get the device, a failed device, for example, like a phone or a tablet battery that is severely swollen, then we look for any mechanical damage, external mechanical damage or thermal damage that might be happening for the device, because these can also initiate the failure mechanism for the battery. But if you do not see anything with our naked eye, then 2D X-ray is definitely most helpful. And then we look for any unusual aspects in the cell, such as like the rigidity of the tabs, or how is the gel roll standing? Is there any crack in the electrodes or components? So we look for these kind of things, and also any region that deformed more than the other portions. And we can also zoom into certain regions, especially the edges and corners, which are more prone to start failure mechanisms because of the additional mechanical stress that they are experiencing during the operation. So we can also zoom into different areas as if needed, and then look in more detail for those areas. So 2D X-ray is actually great and pretty quick, but only drawback is we do not have, of course, the third dimension. So in order to provide that, we can do CT scans. And in this, we get lots of images and then combine them to create a 3D image. And after this is formed, we can take slices for locations that we are suspecting the failure can be initiated, and then look into these cross sections in every axis, like x-axis, y-axis, or z-axis. And in this particular example, you can see this is the most interesting one. So z-axis slice showing us the layers of gel roll, and also on top there is some unusual region which needs further investigation. And then after detecting these, actually these are really helpful, especially when we go to the teardown. We need to be really careful about those regions to not destroy them and analyze them carefully. And what we also do is we can go to the RGA, semi-quantitative RGA analysis, and then we look for the gaseous species, the content of the gaseous species in them. So in here, you see one of the examples that we did. What we do is we put silicon gasket to prevent any leakage, either from inside out or outside in, and then collect the gases. After our carrier gas, which is nitrogen, is being analyzed, we just get the gas from the battery to be analyzed into our device. And then there are lots of information in this analysis, but the key things that we are focusing on is to look for the hydrogen content, because one of the common reasons for batteries to fail is the moisture ingress. So then if the moisture is causing this battery to be swollen, then the hydrogen content in this in the swollen case should be much higher, more than 50%, which is not the case in this one. So in this particular example, RGA helps us that moisture ingress is not related with the failure mode for this one. And then we are looking for CO2 to CO ratio to understand whether there is overcharge or over discharge. And this in this example, you can see the carbon dioxide to carbon monoxide ratio is a little bit above 4, which is pretty low. And in these cases, what we are suspecting is that there might be over discharging, which is causing this battery to fail because of like when there's over discharging, then the oxidation step produces more carbon monoxide than the normal ratio of carbon dioxide to carbon monoxide. But this is not enough by itself, so that's why in such cases we need a full teardown to look for the components. And when it comes to the teardown, we usually use our glow box in order to do the teardown to minimize the air exposure of the samples and components. In some cases, it is also possible to do the teardown in the dry room in a safe manner, but we prefer to do it in the glow box, both for safety reasons and also to keep the sample as it is as much as possible. And then we collect electrodes, anode and cathode, and also the separator. And in some cases, we can also get the electrolyte out in order to characterize it. But in this example, I will just focus on the anode, cathode, and the separator. And during this process, actually, we collect lots of images. These are only a few examples. And depending on the client request, we can take many more and more specific on certain regions. For example, in some cases, lithium plating might be an issue, so we need to focus more on these sort of areas to collect everything that we can. But in order to be fully transparent, we just get images as much as possible for each step. And then after collecting these pieces, then we have a tabletop SEM in the battery lab, so we can quickly check the morphology of the electrodes or the separator, and also check the compositional content of them. So this is just one example image from our SEM, and so we can go up to 10,000 magnification without losing too much resolution. But if more detailed images are needed, we have two options. We can either send the sample to the SEM team in our next building, so we can collect more images, more detailed images from there, or we can just send the sample for NanoLab to collect cross-sectional images through TEM with the use of focused ion beam technique. And this is the example for the second one. And as you can see, the cathode sample is like we got the cross-sectional image from the cathode sample with the use of plasma FEP. And then you can see the current collector in the middle, and then the electrode on both sides. And also we can see how the particles are positioned and what kind of size changes happening for those particles. And we can also compare before and after if the pristine sample is available. So these are really helpful in some cases to understand what's really happening for the battery. And then of course we need to, for this particular project, we need to check the compositional map, because if we are suspecting there's over discharge, then what will happen is the current collector on the anode side, which is mainly copper, so it will start to get dissolved and then go towards cathode and be redeposited in the cathode. So since we are analyzing the cathode now, we were looking for any sign of copper, presence of copper, that would support the result from RGA, so that the over discharge issue will be confirmed. But here, as you can see, there is no sign of copper, which kind of eliminates the over discharge issue, because there should be copper in that case. So if the situation is like this, then we just go to the separator and look for any copper or cobalt content. Depending on the cathode material, it might be nickel, iron, manganese. But for this example, we know that the the cathode had cobalt in it. So we were looking for copper or cobalt in the separator. And as you can see, since this is the separator, there is a little bit charging, but we also have, for SEM images, we also have gold sputtering. So we can also code it with gold in order to look it under SEM, but this image is coming from TEM, so it is charging a little bit, but it doesn't prevent any of the features that we are trying to look for. And under SEM EDS analysis, we can check whether there's copper or cobalt in the separator, and it seems like both of them are missing, which means like the separator is, it might or might not include those elements either through over discharge or overcharge, but this leaves us one more option, which is checking the anode. Because instead, like if there is overcharge, the opposite will happen. This time, cobalt will start to diffuse through the system and dissolved in the electrolyte and be carried towards the anode and will be redeposited on the anode side. And as you can see from this image here and this analysis, there is cobalt presence in the anode, which shouldn't be the case in ideal operation. That's why this is suggesting us that the overcharge is the main issue for this battery to swell. And actually, since this was an intentional project that we prepared, that we forced the battery to fail, we already knew the answer from the beginning, but it was also good to catch this cobalt content on the anode. And in addition to this, what we can do is we can collect the cross-sectional image from the individual components, and then afterwards, by image processing, we can look for the areal fraction of the pores, particles, or binders in between the particles. So as you can see in this example, the particle component is forming the majority of the image, which is above 60%. And then binder is a little bit below 40%, and rest is pore. And more detailed analysis are possible. By looking into the pore size distribution, we can check whether they are uniformly distributed or not. And we can also check the same thing for the particle size distribution as well. And then we also provide electrolyte characterization. So in many cases, we definitely prefer to get the pristine electrolyte for QC control, quality control, but also we can try to get the electrolyte out of the battery and be analyzed and then analyze it. But in such cases, actually, it is, as you may know, it is really hard to get meaningful amount of electrolyte from power cell or cylindrical cell because they are very limited in the amount, and also during the teardown, they get dried and evaporate pretty quickly. But for the analysis, what we do is we can create a solvent and then put the battery inside to get the electrolyte from the system and dilute it in our solvent. And since we know the content of our solvent, then in the analysis we can disregard that part and focus more on the electrolyte contribution. And that's how we can also analyze the electrolytes. So in summary for this case study, there were no mechanical damage or thermal damage for the device. No foreign objects were detected in the 2D X-ray or CT scans. And then the analysis on the pouch and also RGA content eliminated the moisture ingress as a root cause. But then there was a suspicious CO to CO2 ratio, which was actually directing us towards over discharging. But in order to double check and confirm whether this is the situation, we did a full teardown and see there's cobalt in the anode side, which is suggesting us the overcharge was the issue. So this is just one example story. We can do many other type of investigations as well if needed. And also it doesn't need to be a full story. If you only need one step, we are always happy to help with that step as well. And in addition to this, We also have titration technique available in our battery lab, which was not needed for the previous case study. But what we can do with it is, so we can check the moisture content, especially for the electrolytes, by using the Carl-Fisher titration technique, and we can check HF content of the electrolytes, especially after certain shelf life or like for initial production. It is really important to control HF content and limit it below a certain value. So we can do that in ppm level, and then we can also check the carbonate content for some of the raw materials, and we can also do conductivity measurements with our titration equipment. So overall, like, why choose EAG? First, client confidentiality is really core. We really value the confidentiality issue, and none of the data will go public or will be shared with others. So this is really one of the key components that we are trying to that we implement in our every project. And then we offer a multidisciplinary approach, and actually this is not a single site operation. We have multiple sites and over like more than 2,500 instruments. So this is that we are trying to find every answers for materials characterization and engineering. And yeah, that's pretty much it for this presentation. Thank you a lot for listening to me. But if you have any questions, you can always contact us through our website, and we are looking forward to see you here or work with you in the future.